All right. Hello, class. Where'd it go? All right. Hello, class. I'm here with Hazel. I'm happy to report that Bug is feeling better. He was feeling sick yesterday, and he's a happy camper. He's actually sleeping in the backyard right now. I'll post a picture in Discord. It's a really cute picture. So I'm here with Hazel. Your breath stinks. Your breath stinks. Can I get a kiss? Can I get a kiss from Hazel? Hazel. Hazel. What to do? Oh, Bugger. Come here. Come here, Bugger. This is a rare moment. Oh, yeah. Oh, yeah. Got two dogs. Okay. Let's see. I wanted to reiterate from what I said yesterday that I do not want you to overwork yourself. I don't know how much time you have, how much inclination you have to do physics problems. So just do the amount of physics that is appropriate for you given your personal mental state and interest level right now. Because I'm kind of assigning a lot, and I don't really care how much you do. Just do the amount that's appropriate for you and your goals. Okay? So let's get to work on a 2016 Electricity and Magnetism free response. Hey Fu, hey Mo, hey Alex. Alrighty. So let's see. Question one. Ooh, I saw some equipotentials. Ooh, equipotentials. Okay, number one, part A. 2-point charges, Q1 and Q2, are fixed in place on the x. All right. Charge Q2 has a value of minus or plus 2 nanocoulombs. The values of the electric potential are illustrated by the given equipotential diagram shown above. A says calculate the value of Q1. So I'm going to pick. So first of all, let's figure out what the scale is. It looks like I'm gonna draw on this here. I want to annotate it. It looks like the origin is right here. Okay, and so that's the origin. And then it looks like, because this is at -1, it looks like the scale is, this is going to be, that distance right there is 0.5 meters. Okay, so based on the information, I'm just setting the scale. So that's okay. So I'm actually going to choose point B, and I know that point B has potential 0. All right. So because that's the equipotential that it's on. And so I can see that the potential at B is going to be K Q1 over R1 plus K Q2 over R2, where Q1 is the distance, or R1 is the distance from Q1 to the point B, and Q2 is or R2 is the distance from Q2 to point B. So the potential at B is 0, and so what that says, I could divide both sides of this by Q, or by K. Divide both sides by K, that cancels those out, and I still get 0. So I have Q1 over, now how far is Q1 from B? I can see it's 1, 2, 3, 4, 5 grid squares. So that's a distance of 2.5 meters. And then Q2 is 2 nanocoulombs, and it is only 2 squares away. So that would be 1 meter away. All right. So solving that equation, it says that Q1 equals, it looks like minus 5 nanocoulombs. All right. B, at point C on the diagram, where is point C? Oh, there it is. Draw a vector representing the direction of the electric field. So we know that the electric field points perpendicular to the equipotential, so it's going to point along this direction, and it points in the direction of more negative equipotentials. So we can see that point C is on the minus 12 volt equipotential, and down here is the minus 16 volt equipotential. So that minus 16 is more negative than minus 12, so that means that it's going to point sort of in that direction. Okay. So B is done. C says, calculate the approximate magnitude of the electric field strength at point D on the diagram. With the mailman's here. Wonder what mail I'm gonna get. I'll get more packages. I gotta tell you guys, I've been just like, I've been going on abebooks.com. I don't know if you guys know about abebooks.com, but it's good, Hazel. abebooks.com, it's a website where you can get used books, and you can get textbooks, which I like. You can get any books. But I bought a textbook, a used textbook, for $4 with free shipping. It's like, so it's like what, I mean, you know, if you're making minimum wage, you could buy 3 books an hour. It's crazy. I love it. All right. So we're trying to calculate the electric field at point D. So I want to remind you that the magnitude of the electric field is the change in potential divided by the change in position. Point right here. Okay? So I can see that the change in potential is 4 volts because it goes from minus 20 to minus 24. And then it's 2 mini squares. And we know a big square is 0.5 meters. So a mini square is going to be 0.1 meters. So 2 mini squares is going to be 0.2 meters. That's the distance between those 2 points. And so that gives us about 20 volts per meter is the electric field at that location. D, the equipotential labeled 0 volts is the cross-section of a nearly spherical surface. Field is equal to the charge enclosed over epsilon naught. And we can see that for B, this is B, equipotential that B is on. The charge enclosed is Q2. So the charge enclosed is 2 nanocoulombs. So that's 2 times 10 to the minus 9. And epsilon naught is 8 pointer. 2 times 10 to the minus 9 divided by 8.9 divided by 10 to the minus 12. 224 Newton meter squared per. Calculate the work. So let's see. Point A, and then point E. Where's point E? I can't see it. Oh, point E is over here. You can see that point E is on a minus 4 volt equipotential. Okay. So the proton is going to go from high potential to low potential. And so the change in potential is going to be 8 volts. And you might remember that the change in potential energy is Q times the change in potential. So that would be 1.6 times 10 to the minus 19, which is the charge of a proton, times 8. Which gives us 1.28 times 10 to the minus 18 joules. So remember, the change in the potential energy is equal to the work done. Okay? So that's the work done. So that was I. And then part 2 said, well, calculate the speed of the proton when it reaches point E. Well, for that, we're going to use the work kinetic energy theorem, which says that the work is the change in kinetic energy. It started out with 0 kinetic energy because it was at rest. So the change in kinetic energy would just be the final kinetic energy, which is 1/2 mv final squared. Mass of a proton is 1.7 times 10 to the negative 27. It's just a handy-dandy thing to know. And then the work is 1.28 times 10 to the minus 18. So we can solve for V final, which I will do. And I get 3.9 times 10 to the 4th meters per second. And it just keeps going. This question just keeps on going. An electron is released at rest from point B. Which one of the following indicates the direction of the initial acceleration, if any, of the electron? So what we can see is that at point A, the direction of decreasing electric potential is this way. So the electric field is pointing to the right at point A. Electrons, so you might recall that F equals QE. Electrons have negative charge, so they go in the opposite direction of the electric field. So there will be a leftward force on an electron, which means its acceleration will be to the left. This is neglecting gravity. You know, gravity might point down, or I don't know which way gravity points in that picture. All right, so we're moving on to question 2. Looks like we got a circuit. What do you want to bet, class, that if I scroll down, we're going to see the circuit redrawn with a capacitor? What do you guys think? Oh, it's not. Okay. So this has no RC circuits. Interesting. Circuit above consists of a source of variable EMF E, an ideal ammeter, an ideal voltmeter, a resistor of resistance big R and a sample of wire with the resistance little r. How does the current through the wire sample compare with the current through the resistor R? Well, the voltmeter, okay, voltmeters are just there on the side. They're not changing the behavior of the circuit at all. So we can just ignore the voltmeter, okay? And if we ignore the voltmeter, we see that this is just a series circuit, okay? So since it's a series circuits always have the same current, so it's going to be the same through both. Okay, so this will be your answer. All right. B, how does the potential difference across the wire sample compare with the potential difference across the resistor big R? That's not a very great question, in my opinion, because it's sort of asking you. So, oh, we got some new people here. Hey, James. My forge, actually, I already did get a package today, and it was my heavy-duty heat-resistant gloves. So I can show you my heavy-duty heat-resistant gloves if you want to see them. So these are actually welding gloves, but they're good to, like, you know, they're heavy-duty gloves. All right. So where was I? So this circuit is basically a potential divider. Okay. Okay, now the mail actually came, so now I gotta look for the mail. Sorry about this, guys. Nothing of interest. So, all right, so one of the equations I taught you, if we think about this, the current that's going to flow in this circuit is E over little r plus big R. Okay? That's the only current in this circuit. The voltage across the little r resistor is going to be I times little r. So it will be E times little r over little r plus big R. Okay? So this is the voltage across the little resistor. And depending on the resistance of little r, this could be more than 50% of the voltage, or it could be less than 50% of the voltage. So I'm going to say it depends on the resistance of the sample. So that's really the truth. But the fact that it says it's a wire, that kind of indicates that the fact that it's a wire indicates that it probably has a very small resistance, but it doesn't explicitly say that it's smaller. So if the wire does indeed, as we would expect, have a really small resistance, then it would be greater across big R. So I kind of think that there's two right answers depending on what assumptions you make. With the sample of wire in place, the EMF of the source is set to a given value. The current through and the potential difference across resistor big R are measured. This is repeated for several values of the EMF, and the data are recorded as shown in the table below. Indicate which quantities should be graphed to yield a straight line that can be used to calculate a numerical resistance of the wire sample. Okay, so what I'm going to say is the voltage across big R is going to be the same equation as this, only it would be I times big R. So it's going to be all right. So it's going to be epsilon times big R over little r plus big R. So that's the voltage there. Okay. Getting a little mixed up here. We know there's a couple ways we could do this. Okay, so this is V sub R. All right. So why not? So I'm going to go ahead and put, so this is the way I'm going to do it. This is a little bit of a weird way. I'm guessing that the answer in the book is going to be in the... I agree with what you said, Christian. That's a good comment regarding the answer to part B. So that means that if I put V sub R on the vertical axis, whoops, and I put E on the horizontal axis, the slope would be big R over little r plus big R. Okay? So what I'm going to do is on the horizontal axis, I'm going to put E. And then on the vertical axis, I'm going to put V sub big R. Okay. And then if I do that, I can see that the slope is if I do this, I can see that the slope is big R over little r plus big R. Now, what is big R, you say? Well, big R, wouldn't that just be volts across big R divided by current of big R? So I can use any one of these rows to calculate the resistance of big R. So if I use this first row and I use these two numbers, whoops, that's going to give me I have 0.179 over 0.162. And that gives me that big R is equal to 1.1 ohms. So my slope is going to be 1.1 over little r plus 1.1. All right, so that's going to allow me to solve the problem. So if I plot the data, so 2.5, 1.79. So 2.5, 1.79. So this is my first point. So I'm having on my scale here, I have 0.2 amps, or 0.2 volts, excuse me. And here I have 0.25 volts. So, all right, so that's what I'm using to set my scale. All right, and then my second point is 0.5 and 0.335. So here would be that, so maybe like right here. And I'm just going to do one more point. The 1 volt point is 0.67. So 1 volt would be over here, and 0.67, this is 0.2, 0.4, 0.6, 0.8, 0.7, 0.67 is somewhere around here. Okay, so I can see I have a linear graph. Whoops. So there's my slope. I can see that the slope has maybe a, so I can calculate the slope quite easily. It looks like it's maybe the slope is going to be, I'm using this point. It's going to be maybe 0.5 over 0.75. So that means, and I get that little r equals 1.1 minus 1.1 times 0.67 over 0.67. And I get that little r equals 0.54 ohms. Okay. So that was part E. Now I'm going over to part F. Let me make sure you can see that. Part F says the wire sample has a length of 3 meters and a radius of blah. Calculate the resistivity. So resistance of a sample is rho L over A. It's a circular cross section, so the area is pi r squared. We just calculated the resistance, so we have 0.54 is equal to rho times L over A. Okay. So that gives rho equals 5.7 times 10 to the minus 7 ohm meters. G. Suppose the ammeter is used to collect the data was not ideal. Would the actual value of the resistance of the wire sample be greater than, less than, or equal to that calculated in part E? What does it mean to say that an ammeter is ideal or not ideal? Ideal ammeters have an infinite resistance. So no current can flow through the ammeter. No current flows that way. All right? But if it's a non-ideal ammeter, some of the current flows through the ammeter. Okay? So notice how if the ammeter is not ideal, it provides an extra pathway for the current to flow, which means it's going to reduce the resistance of the circuit, which means that the current in the circuit is going to go up. And if the current in the circuit goes up, then that means that, if the current in the circuit goes up, then that means we're going to have a bigger voltage drop across little r. Okay. And since let me think about this for a second. Now I'm forgetting what the question is. Suppose the oh, it said the ammeter is not ideal. My bad. Oh, this is just part 2. Okay. So let me do part 2 first. It says, if the ideal voltmeter is replaced by a voltmeter that is not ideal in the experiment is repeated, would the readings on the ammeter be greater than, less than, or equal to those in the data chart before part C? Okay, so I actually answered that because I said the current would go up because the apparent resistance would be less. Okay. So now part I says, what if the ammeter used to collect the data was not ideal? Would the actual value of the resistance in the wire sample be greater than, less than, or equal to that calculated in part E? As far as an ideal ammeter is concerned, an ideal ammeter does not prevent current flow at all. It has a resistance of 0. A non-ideal ammeter has a resistance, okay? And that resistance is going to basically reduce the amount of current that flows in the circuit. And it's like the resistance is added into little r. So what we're going to get is the measured little r is going to be greater than the actual little r, because this measured little r is actually going to be its actual resistance plus the resistance of the ammeter. Okay, that's what you would be measuring. So let's see, what does that say? So I would say the actual value would be less than. Okay. Part 3. A conducting bar of mass m, length L, and negligible resistance is connected to 2 long vertical conducting rails. So we got another railgun problem. Hopefully you guys are starting to see patterns. We get a electric field problem, we get a magnetic field problem, we get a circuits problem. Because magnetism is not on the AP Physics C exam this year, I don't think. I think I'm going to skip this one for today in the interest of time because I'm already late on my lesson. Because this is the magnetism one. So I think I'm going to stop there actually. But I encourage you to work that out on your own. We already did a railgun problem as well in one of the earlier free response questions. So starting tomorrow, we're going to review mechanics. Okay? So I hope you guys have a wonderful afternoon, and I will talk to you tomorrow. Bye.